start. And so welcome to everybody to the final conference of our long workshop on worksheet from a string theory perspective. So this is the 10th string field theory conference that we hold, and it's devoted to string field theory and string perturbation theory this year. And our first speaker today is Loriano Bonora from CISA, and he's going to tell us about the worldline approach to theories with infinite many fields in flat spacetime. Thank you very much.
Thank you. I'm very, very glad to be here. I would like to thank the organizer of the workshop for inviting me. And especially because this is the first talk of the workshop. Which, the title is a long title because I think it would be much simpler to call it higher spin theories in flat space-time, but some representative of the community of higher spins, they say that the theories I'm going to talk about are not higher spins, so okay. But anyway, we will see. You will see, you will judge. Okay, so let's go. Let's start. These are my collaborators. Stefano is here among the participants of the workshop. And this is a series of papers we have been producing in the last 2 years on this subject. What I'm be talking about is try to talk not as much as from the point of view of worksheet perspective, but from a sort of mini version of the worksheet, which is the worldline. And then at the end, perhaps we will see how there could be a connection with the worksheet. So the talk is about the effective action approach to create these theories and the extractions of the effective action properties. Then I will talk about a symmetry, properties of these theories, which is called L symmetry, which many of you are familiar with, but I think it is important to stress the presence of this symmetry here, because it looks like it is a sort of signal that the theory is a good theory, is consistent. And then I will talk more specifically about higher spin theory, higher spin, what I call higher spin Yang-Mills-like theories, and comment about their properties, and finally argue that these theories are good behaved and they do not contain ghosts in particular, because the problems of theories containing all the alternative theories of gravity as usual is the presence of ghosts. So, well, I start from the historical point of view. So, I personally was very much struck by a paper that appears a few years ago, in which the authors argue that in order to describe gravity with matter fields together, it is compulsory to use infinite many fields. Otherwise, you contradict causality. And so the problem question that I was interested in is the following. Are string theories the only ones that satisfy these conditions, that they are consistent, or are there other theories? And in case that there are they related to string theories, or are they completely different? Other questions are, for instance, can they exhibit critical dimension or not? And have they good ultraviolet convergence properties as string theories, or are they completely different? Well, I will not be able to answer all these questions, but to start with some examples. First of all, how can we construct other candidate theories which contains infinite many fields, that is infinite many spin? So for brevity, let me call higher spin theories, okay? One method is based on the effective action. We realized this by digging out from the literature things that should be very, very well known. For instance, if you go to three dimensions and consider a theory, a spinor theory coupled to a gauge potential, a mu, which can be non-abelian in this case. And then there is this current, which is classically conserved, okay, covariantly conserved. These have been studied by many people in the past. We can construct this theory, the effective action, by considering the endpoint function of this current, of these conserved currents, and plugging into this formula, this what the result is a conserved, the result is an effective action. Now, so the point is to calculate 2-point function, 3-point function, and point function, and so in order to describe completely the effective action, of course. Okay, here is the on-loop conservation laws for 2 or 3-point functions, but what I am interested in now is another thing, is to study the 2-point function, and which is very simple, it's written here, and to go to the infrared and ultraviolet limit. In the infrared limit in particular, we find this behavior, and if you plug in this result into the previous formula for the effective action, which is this, what you find is the first term of the non-abelian Chern-Simons theory. But there is more. If you go, instead of taking, okay, I forgot to say, of course, this theory, since it contains a mass, breaks parity in 3 dimensions, or at least reflection properties, the reflection properties. And so there appear parity odd terms, as in this case. Oh, sorry. There appear parity odd terms, but there is also an even sector, which is this. And if you study the even sector of the 2-point function, and you go to the infrared limit, you find the following result. And if you plug in this result into the effective action, you find that this is the term, the lowest term in the expansion of the EME section. And so we ask ourselves, but is this a general fact, or is it just an accident? And so if we go on to spin 2, we find a similar property. That is, we couple this to a metric. And again, in this case, the relevant current, conserved current, is the energy momentum tensor. And you find the 2-point function of the energy momentum tensor. You find this expression. When you calculate this in the infrared and ultraviolet limit, you get 2 terms. The parity of terms, which is this, and this gives rise to the first term, the lowest order term of the Chern-Simons theory. And if you go instead to consider the even sector, you find the first term of the lowest term of the Einstein-Hilbert action. So again, these are well known, and then one asks, but can we go on with this exercise? No, let us consider there are other currents. It's very easy to construct conserved currents of higher orders, and this is the conserved currents for the third order symmetric tensor current, which we couple to an external field like we did for the gauge field and metric. And this term is invariant under this infinitesimal transformation. And what we find here, if we study the effective action again the same way as before, at least to the lowest order, that is the quadratic order, what we find is the 2-point function has this form. And this is the parity odd term, and this is the parity even term, parity even 2-point functions. And when we consider the action that they give rise by plugging this result in the effective action, what we find is this. And this is something well known because it's a generalization, a slight generalization of an action proposed by Poppenthausen a long time ago. Well, this is for the odd part. For the even part, we find something like this. We find that the two-point function, we find that it gives rise to this action, which is non-local because it has this 1 over D'Alembert term. And this gives rise to these equations of motion, which are non-local equations of motion. But if we take the trace of this, okay, the underlying index means that they are symmetrized. I take the trace with respect to two indices. This equation, you will get this equation, and upon replace this into the one gets precisely the non-local Frosdal equation for massless 3-spin. What is the non-local? Perhaps I should spend some time explaining what is the non-local Frosdal equation, which was proposed a long time ago for the spin 3 field, which is this, where, again, this is the symbol are expressed, as I said before, they mean symmetries. If I take the variation with respect to this transformation, I get the following result. So this is invariant if we assume that the gauge parameter is traceless, which is not a very pleasant thing to do. And so Franz and Sagnotti studying this problem, they found that they decided that it was possible to accept non-locality in this form. So this equation. This is invariant without imposing any constraint, but it is non-local. However, this non-locality is irrelevant, is a gauge artifact. In fact, they introduced a compensator field alpha in this form, which transforms everything in local things. And not only, but this is Lagrangian, that is, we can construct a Lagrangian for the field phi and the field alpha. So that in the end, a local Lagrangian, so that in the end the non-locality in the initial equation is only a gauge tail, which guarantees simply the gauge covariance. Okay, this is just to remind you a few examples, and they've been generalized. Even in our case, we went on with this program, and we studied not only the 3-dimension, but 4-dimension, 5-dimension, etc., up to 8-dimension, in sometimes in any dimension, and we find the same result. That is, you find this equation, essentially, a gauge equation, or gauge, gravity, and higher spin equations of motion in the effective action. And you find instead Chern-Simons actions in odd dimensions. And this seems to be very general. So the question is now, if we want to construct a higher spin theory, a very general one, this seems to be a method, but you have to go on with the calculation how to find the interaction vertices, and so you have to calculate diagrams like these ones, which becomes very complicated to evaluate and to deal with. So this method is certainly something that is valid in order to construct higher spin theories. It requires two basic ingredients to have conserved currents, but this can be easily done. And also it requires to define symmetry transformation. Now, in the previous example, I showed that the transformation like these ones, they are at the first order. Oh, no, sorry. I went the wrong way. For instance, these transformations, they are only at the first order. And so we don't know how to go on with these gauge transformations. To explain, And this is one of the big problems of this, that many people, like these people mentioned, try to solve. They have been trying to solve. Sometimes they did. They solved it in some explicit examples in 3D and 4D in ADS and 4D ADS. But there seems to be, well, much has still to be done. I mean, there are... So, but in fact, following the simple method that I mentioned before, that is calculating the Feynman diagram simply of a theory with external field, seems to be very complicated. And one has to find a systematic way to solve it. And this systematic way, this more systematic way, say, because it's not the end of it, is the Worldline Quantization. The Worldline Quantization means that you consider fields, but these fields are a function of x, and x is understood as the coordinate of a particle, of a quantized particle, with the Weil quantization method. This has a long history, and many people working on it. Also, the formalism is, I remember, a few basic formulas. In this case, remember when you have the Weil-Wigner quantization method is based on a set of operators, quantum operators, and their classical symbols. The symbols are defined in the phase space, not in the space-time only. They are a function of x and p. And the correspondence between the operator and the y quantity is given by this, what x and p, x hat and p hat, are the position and momentum operators. The product of operators corresponds to the star product of the symbols. This is the rule. So, and the star product is the Moyal product, which is written here. This product is associative and has a trace property that is, which is written here. That is, when you integrate over the phase space and you have this star product between two factors, you can drop it. Okay, so let us apply this to the previous example, that is the spin in any dimension this time. So we have a spinor field, which we represent as operators. No, this is the simple model that we write usually in space. But then we replace this with operators, and we represent it in this way, where P is the quantum is the momentum operator, psi are the vectors, say, stated in phase space, and gamma is the gamma function, and H contains an operator whose symbol is represented by this infinite set of fields, of symmetric fields. Well, they are symmetric in mu1, 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 but not in mu, of course, in general. Oh, no, please, please. Sorry?
Is it allowed to ask a question? Okay.
Okay.
I have two questions.
Yes.
So one is that, so you are using this method to generate action.
Yes.
For the higher speed field. So this is one way of constructing gauge invariant action, and because we start.
Yeah, this is what I think.
Is it most general in the sense that, for example, if
Yeah.
you just want to construct the most general action, which is in terms of derivative expansion, does this cover all these terms?
I don't know if it covers all, but it covers most, a very large portion of them. Well,
Of identifying invariant action.
right, right. But they are non-local in general.
Yeah, I understand. And
Yeah.
another question is that, so you want to introduce how this can be extended non-linear.
Yes, yes.
So how is that compatible with Coleman material theory?
Ah, okay, I will talk at the end. Yeah, yeah. Yes. Okay, so Okay, so at the end, the action expressed in okay, this is an integral over x missing, sorry. the full action is given by this expression here. So, where the currents are given by these very compact expressions, for instance, the first current is this, the second current is this, and so on. And what is more important is that S is off-shell symmetric. This is important, off-shell symmetric under this transformation, these gauge transformations. You see, we should take out the gammas, of course, and we have an index gamma A or mu, and we have the dA, and here HA, and this looks very much like an ordinary gauge transformation, except that this is made in the phase space and with the star product. As I mentioned before, the star product, this means that it contains infinite many terms, infinite many derivatives. Okay, this is the other transformation. And here we can, we can define the effective action. Well, this is an example. I mean, it's not very important in the context of I am talking about, so I will skip it. Only you can construct in this way, of course, the amplitudes of this, and this is an example. The advantage of the new method is, of this new method is that the Worldline quantization method gives directly the conserved currents. Yeah, you don't have to create them, they are already there, offered by the formalism, and also, and especially the symmetry transformation, they are there. You know already that the model that will come out by integrating out the spinor field will be invariant under these transformations. Okay? Modulo, of course, anomalies that can be there. Well, with the Feynman diagram techniques that I mentioned at the beginning, it does not determine the conserved current. You have to work and take them. But this is a very, it's not very important problem. The point is that you don't know the gauge transformations. You have to continue by trial and error to create the next term and so on and so forth. And of course, is an exhausting exercise. At this point, I would like to mention that the properties of these models that come out from this treatment, which is the L infinity symmetry. The effective action is this, of course, where these are the amplitudes of the currents, as we did before, but now they are integrated also over the momenta. And varying with respect to t, we obtain the so-called generalized equation of motion, which are written here. The first member of this equation transform in covariant way. And this is the basis of what is called the L infinity symmetry. L infinity symmetry is a symmetry in which you have spaces, vector spaces, which in this case they reduce to 3, and they're called x0, x1, x minus 1, x minus 2, minus 1, 0, minus 1, minus 2 is the degree, which is given to these parameters x as degree 0, h as degree minus 1, and f mu nu as degree minus 2. F mu nu is the equation of motion, I recall you. And the relation to be satisfied in order to be sure that L symmetry is there, L infinity symmetry is there, is this, which looks very complicated, but in detail becomes this. So they are products, these are products with many entries, and they may consider products, and they have to satisfy, these products have to satisfy these things, these relations. And now, by defining L1 in this form, L2 in this way, Lj with an epsilon inside equals 0, but Lj with Ln with many h's is given by this complicated expression. Well, if you use the properties of this theory, you will see that if you use these properties, especially the gauge transformation, which and the transformation of the equation of motion, which can be decomposed in this way according to the various powers of h, then you see that L infinity is there. I mean, it's satisfied. So, and L infinity is a very important ingredient apparently. We don't know, I mean, at least I don't know exactly what is the foundation, but it is a fact that in all the good gauge theories, Chern-Simons theories, double field theory, closed string field theories, they have this property, this infinite symmetry. Probably some of you will be talking about it later. But also these Worldline Quantization quantum field theories that we have introduced in terms of effective actions, they satisfy these properties. Okay, I recall you now, however, that in general, so this method produces automatic and high spin symmetric theory, but in general what comes out from this procedure is a non-local theory. Non-local in the sense, probably, in the sense of which I mentioned at the beginning, that is a non-locality which is functional to the fact of proving gauge invariance, but then if you go close by, you see that it is an artifact, in fact, it's not a real non-locality. But in fact, the fact is even if they are local, they have infinite many derivatives. Okay, the idea now is to try a shortcut and see that integrate L infinity symmetry. What does it mean? It means finding a local theory, local but infinite, with infinite many derivatives, which satisfies directly the L infinity symmetry, that is the previous axioms. And this can be done. It is perhaps even too easy. Let me show you why. Okay, the higher spin gauge transformation in this one, I have shown it several times. If we expand in terms of in U now, since I have to mention, later on I have to mention the physical momenta, external momenta, I will change the symbol of P into U. U is the momentum which we quantize the X and U. So we expand in U, and we find various local fields. And the same we do for the parameters, for the gauge parameters. And in components, you see that this transformation means this. They are infinite long expression. They have infinite many derivatives. And now, if we denote, now this lends itself to interpretation in terms of gauge field and Firmine. If we define, okay, if we transform the ordinary gauge field in this way, okay, this is the tilde that means the ordinary field, okay, the ordinary gauge field, an ordinary gauge field, not the one that I introduced, but an ordinary one. And the transformation becomes this. And for a tilde, which is the inverse Firmine, the transformation is the inverse Firmine. The transformation is this. Now, if you compare this with the previous transformation, you see that we can make the identification that the previous field A, gauge field A, coincide exactly with the ordinary gauge field in terms of transformations. And the previous Firmine coincide with this Firmine here. So that they lend itself to an interpretation in terms of gauge theories, but also containing gravity. Well, let's see. Okay. Here is some recall of the same properties. So this is the gauge field, the field, the inverse Firmine. So the direct Firmine is an infinite expression. The curvature is this, the inverse curvature is this, the inverse curvature, the inverse metric is this, the metric is this. And so in terms of metric, actually is an infinite set of expression, although the theory that we will see is at most quadratic in kind. Let me see why. Okay, how do you consider? Well, as I said, It is even too easy to construct a theory like this, because if you construct a field strength, the field strength GAB like this, which is the analog of a field strength in gauge theories, it transforms in this way, in a very simple way. And so if you introduce this functional, this is invariant under this gauge transformation. It's completely invariant. I denote this, this double bracket as the double integration with respect to x and u. Now, however, regarding this double integration, remember that the dynamics is in x, is in space-time, not in the phase space. U is simply a counting device. It's like, imagine that you replace it with the infinite summation, for instance. Okay, now taking the variation, we get the following equations of motion, which can be written down in details in this form. Okay? These are the infinite many equations of motion of any spin. And in case that you have a pure U1 case, you get this equation, which is the usual equation. If you impose the Landau gauge, you get this equation, the usual gauge fixed equation for a gauge field. In gravity, you get this, which is different from the usual ones, but you can impose the gauge, Landau gauge, and you get this again, and so on and so forth. You can go to spin 3, spin 4, they are all interaction. But remember, in this theory, the interaction is at most quartic in the fields. Okay. Now, there is a problem here, because if you look at this theory, for instance, at a gauge theory, you limit this approach to the gauge field, for instance, you get FAB, and you transform by a local transformation. You get these additional terms which do not vanish, even if they are integrated over X. So this violates local Lorentz invariance. But the point is more subtle. The point is that this theory, the theory that I showed you before, it comes with a fixed local Lorentz transformation, a gauge fixed local Lorentz transformation. But you can immediately restore the local Lorentz invariance in a very simple way. That is by introducing a trivial frame. A trivial frame is defined by the fact that if you multiply it by a local Lorentz transformation, OAB, you get a delta. A full gravitational frame is the sum of a trivial frame and a non-trivial one which contains the dynamics. Now, with a local Lorentz transformation, we can transform this by doing the inverse of this. You can transform this into the field bind that we saw before, which was here. Ah, no, sorry. I went the wrong way. For instance, this field bind. Okay? Here. This field bind here. They coincide. In the same way, one can introduce also a trivial connection that is given by Lorentz transformation. The curvature of this trivial connection, of course, vanishes. But they are useful in order to restore local gauge invariance. And the simple thing, a rule that you can, the simple recipe to restore local Lorentz invariance is this. When you find in an operator an index A, a flat index A, you replace it with this way, in this way, with the trivial field bind. And you replace any ordinary derivative with a covariant derivative with respect to the inertial covariant derivative, the one that I have just, the trivial derivative, the trivial connections. This, even in the Moyal product, there are infinite many derivatives, but every time you find a derivative like this, you replace with this. Then you can see that in this way, Lorentz invariance is automatically restored. This scheme, which is the separation between inertial and gravitational parts in the frames, and the connection is called teleparallelism. It's a scheme that has been considered, was considered at the beginning also by Einstein, but then he abandoned it. But it is very useful in this context because it allows you to restore local Lorentz invariance. Okay, let's go on. We can also introduce matter fields, scalar master fields, which I call master fields, to distinguish them from the ordinary fields, because they depend also on the momentum, like this. Their gauge transformation are given here, and a covariant derivative is given in this form. This mimics exactly what happens in ordinary theories, of course. There is nothing very original here, but the fact that the formalism works, this is the spinor master field you can introduce also with another covariant derivative, which is this. Okay, and you can BRST quantize this theory by introducing ghost, NRD ghost, and an auxiliary master field B, and you write down the action in this form. This is invariant under the well-known BRST transformation, which continues to be valid also if we replace the ordinary product with the star product. By the way, this theory you can introduce sort of non-abelian gauge fields, if you wish, a non-abelian version of this. I don't have the time to illustrate this, but you can do this. Okay, if you integrate out B, of course, you obtain this gauge extraction, which I will use later on. But even more, you can also mimic the X mechanism in this case. Okay, all the fields that I've considered so far are massless, but you can endow them with a mass by introducing a scalar field phi, the one that I just introduced, with the traditional potential like this, while the ordinary product is replaced by the star product. And then assuming that the field phi 0, okay, which I didn't go to the spreadsheet. Okay, phi 0 is the first field in the series, in this series. Okay, the first without indices is phi 0. And with this value, I mean, they are the usual one. Next, it is more useful here to define finite gauge transformation instead of infinitesimal, which are written here, so that we can parameterize the field phi in this form, where phi 0 is this, and omega is this field, in which the first term is missing. Then the potential becomes this one, for the field phi, for the fluctuation phi 0. And we define a new master field H prime. And if you go to the kinetic term for the scalars, this becomes this one. And you will see that they produce a mass term for the gauge potentials. So the scalar, all the scalars except phi 0, have been eaten by the gauge field that become massive. Okay, this is not just to say that all this works. But now the question comes, this was essentially at the classical level, except for the BRST quantization, but okay, also this can be considered classical in a sense. So we conclude that we can construct classical equation of motion and also interaction for a massless high spin field in any dimension in Minkowski spacetime. And so this seems to contradict the well-known no-go theorems concerning high spin theory. This no-go theorem claims that an interacting massless high spin theory in Minkowski spacetime cannot exist. So what is the problem here? Well, there are, in fact, if you go, there is a plentiful of no-go theorems, and they are different in scope, and the first was probably the one by Weinberger, then came Coleman Mandula, then Witten, then many others. The first, some of them concern the S-metric statements. Some concern theories with a finite number of fields, and most concern theories with minimal coupling to gravity. The highest spin gauge transformations that are considered in many of these are different from the one that we have considered here. And the equation of motion that have been considered, for instance, in this no-go theorem by these authors, they are based on Fronsdal equation of motion, which are different from our equation of motion. So there is room for escaping these no-go theorems, because most of these conditions are evaded by our model. But this doesn't mean that the theory is consistent, of course. It's not enough. One of the main properties that, or the main objection that are raised in this case is, well, okay, you construct a theory, but this theory certainly contains ghosts. This is, yeah, thanks. This is what usually, rightly, people object. So the first thing that we have to verify is to be sure that there are no ghosts in this theory. And I will show you now an argument that goes in that direction. So in order to do that, we have to really quantize the theory, that is, defining the perturbative theory if you are not able to do it in a different way. So we define. And so in order to define a perturbative quantization, we have to get rid of the U integration. This is done by rescaling the fields, by extracting. Remember that U is a momentum, so it has the dimension of a mass. So we extract a mass here, M, curly M, and from this, and we will use it as a parameter, as a mass parameter in the following. And we redefine the fields, and we redefine the coordinate, and also the coupling. If we do this, we can factor out the integration over U, because the integration over U reduces to this. And so it's an infinite constant, of course, and but this is not important in terms of, we throw it away simply, okay? We divide by another infinite constant and we get rid of it. And here is an example of the cubic term. There is also a quartic term, the beginning of a cubic term. There are many other terms, of course. Okay. Yeah. Now, in order to see whether there are ghosts, one has to verify that the propagating modes are the physical ones only, and not other unphysical modes, or even more ghosts. That is, by ghost, well, there are many signification, many meaning given to this term ghost. So I would like to be clear. I use ghost as father of ghosts, but this is a story. They are good ghosts. But they are ghosts in the sense that they have, they are propagating, but their residue is negative. These are dangerous ghosts. And there are also ghosts in another sense, that they have a mass which is negative. They are tachyons, in fact. So this is the animals that appears when you try to quantize alternative gravity theories. But what I want to show is that it is possible to avoid all this. Okay, so so this is the expression for the quadratic part of the actions that we consider. These are the fields. I remember that mu represent the set of symmetric indices, mu and u. KAB is the kinetic operator, which is written here. You see, you recognize very easily here the usual kinetic operator for gauge theories with a gauge parameter alpha. But these are multiplied by a matrix which is infinite. This matrix is given here. Now, if you try to invert this matrix, this is not invertible. And this is the first obstacle that you find. It is not invertible. But it's very easy to get rid of the the dangerous term, it is enough to impose that these fields here are in the indices mu and nu are traceless. And this is a further gauge condition because I have imposed already one here, but we have to impose another gauge condition in this form on the propagator. Once we have done this, now we can invert it and we define M, the matrix M, to be the inverse of N, and it takes the following form here. Now, where delta is this operator here, where with all the permutation in mu and nu, and this operator is nothing but the identity operator in the space of completely symmetric tensor of order n. So that finally the propagator is this. Of course, this is not enough because in between this term, I have eliminated the traceful terms, but this is not enough because among these, if you lower the indices here, there are eta mu nu, and eta contains negative normal states. So you have to make sure that you can get rid of this. Now, this can be done in the following. Let us consider, again, this identity operator. This can be decomposed, well, it's almost a theorem, so I do not insist very much. This can be decomposed into projectors. Projectors according to the various representation of the Lorentz group. So let me introduce this. This is a projector, an elementary projector, B mu nu, which is transverse. This is omega mu nu, which is not transverse, means that, of course, that when you saturate with K mu, you get 0. And these are their properties. Now, in the case n equal 2, which is the first relevant case, you can decompose this into the sum of 4 projectors, which are written explicitly here. This is nothing new because they were already obtained in the literature a long time ago by Stelle, Venoz, and other people. These projectors are all orthogonal to one another. P2, the first is transverse and traceless, is the highest spin 2, say. 2 is transverse and traceless. P1 is traceless but not transverse. P0 is 1, is transverse but not traceless, and P0 bar is neither transverse nor traceless. So this is and you always have these kind of things, okay? You can decompose the identity into this kind of. Now, the important thing is that only these, the terms corresponding to this, propagates. And this can be done by replacing, this is the example for the 3, okay? For n equal 3, for instance, you get P3. Becomes more and more complicated, of course, but it can be done in general for spin, for generic spin. And now here again, P3 is the highest projector, highest spins projector, is transverse, is traceless, and all the other are either non-transverse or not traceless. So the idea is that what you can do is that you can use the fact that these projectors are orthogonal and replace delta with this projector. And so you make sure that only physical modes propagate and that no physical modes are left out. Okay? So that what you find, for instance, for the 2-point function for traceless transverse mode is this formula where you see this propagator, this projector that I mentioned are there, and they guarantees that only physical modes propagates and no physical mode is excluded from the propagation. So this is, in my opinion, is a very important argument in favor of the fact that no ghost exists in this theory, and that you can, of course, this is not an elegant formulation like a Fadepov ghost. This is still to be done. We are working on it. But it requires more and more work. But it's the problem that, this theory is free of ghosts at least. Of course, it may have other problems. a trivial problem would be that the theory is trivial, simply trivial. That is, the S metric is trivial. But okay, actually, I'm more optimistic. I think it's not trivial, and perhaps it's even renormalizable. So that is interesting to continue to study it. Now, in the last 5 minutes, 4 or 5 minutes, I would like to well, not to answer, but to address the question that I mentioned at the beginning. Is this related to string theory? This is, well, since the fields are massless, the first analogy that comes to mind is the tensionless strings. I remind you what the tensionless strings are. Is the limit of string field theory, open string field theory, when alpha prime goes to infinity, open, well, in this case, open string field theory. And in this case, all the Virasoro generators are rescaled. And one obtains the reduced generators so that the Virasoro algebra becomes almost trivial. And you can do the same for the ghost, and you have such simple expression for the BRC generator. And in this sense, the action reduces essentially to the free action, apart from some, say, I don't know how to call it, topological zero mode. Francia, Sagnotti, and Sulaya, they proved that in this way you can make contact with Fronsdal theory by constructing the fields of this kind, okay, phi, d mu, and c mu. And they proved that the equation of motion of string field theory reduces to this for these fields. And then by working out, you find this, which is the early equation that I showed you at the very beginning, with a compensator alpha, which can be absorbed into dynamics. So so that the theory becomes even Lagrangian, say. So this reduces tensionless strings to a particular higher spin string. There is no critical dimension in this theory. But you will see that it doesn't have interaction, so it cannot be related to our theory. They reproduce Fronsdal type equation, and they are not the same as what I showed you before, these higher spin Yang-Mills-like theories. So what are these? Well, I try to, I'm working, this is very work in progress, so I mean, it's just an idea, is to consider another type of rescaling for the creation operator, which is an aggregation operator, which is given by this rescaling by some parameter L, and so that all the ghosts are, all the Virasoro generators are rescaling in this way, so that, and these represent an automorphism of the Virasoro algebra. The Virasoro algebra remains the same, and in the same way, if you rescale also the ghost, also the BRST operator remains the same. So, I mean, it's interesting to look at the states and see whether we can split them according to this parameter L. We can create a state of this kind, another state of this kind by introducing another generators, and so on and so forth. And they scale in this form. They scale differently, of course. And now, if you construct the master field in this way, with the previous local fields, phi, h, a, b, etc., now you construct a master field, and you rescale u according to, with the same parameter, what you get is scale in this form. And so you can, in a sense, isolate the space of master field according to the powers of L, and look at what, if they in a sense, you slice, you reduce to slices the state of string theory, in this case of string field theory, according to the powers of L, and reorganize them in terms of master fields. Now, are there local field theory, local in the sense that I mentioned before, in this case? Well, for what I know, only for phi, for the first and the second, there are local field theory. I tried with the third and more complicated ones is even worse. But there is no way of writing, according to this scheme, of writing a local field theory, even local field theory with infinite many fields. The question is, are these field theories in accord in some way with open string field theory? Is a question that I would like to be able to answer, but for the time being, it's very complicated. Okay, thanks. Yes.
Essentially, you are considering theory professionals with composite operators.
Yeah.
You are making the coefficient of composite operators.
Yes.